And just to finish off, it's worth noting that these are not the only experiments that provide these results. These are sort of the gold standards. They provide some of the best results, but they are not the only things that do it. For example, you can measure distances with other techniques. For example, people have attempted to do this using gamma ray bursts. And these are things which are even brighter. Really can't write today. Even brighter than supernovae. You can see them even further away. That actually in some ways makes them hard to understand. They're actually very variable. Making them standard is very challenging, but people have tried to do it. You can measure distances to quasars, which are supermassive black holes. Using a technique called reverberation mapping, which I will not explain. You can even use gravitational waves as distance measures. And in a sense, none of these are as good as the gold standard at the moment of the Type 1a supernova, at least for direct distance measurements. But nonetheless, they all paint the same picture, which is a consistent picture in which the universe is accelerating and dominated by dark energy. And you can also ask yourself another question when you look at this plot up here. You can say, well, how do we know this has to be dark energy? How do we know things aren't just evolving? And so one thing you can do is you can use other probes, but there is also another acid test that exists. And that is the following. The universe transitions from acceleration to deceleration. Totals 0.7, about redshift 0.7. So redshift 0.7 is out here. So at this particular point in 1998, that was more or less where the most distant Type 1a supernova were known. But now there are big surveys with the Hubble Space Telescope, for example, that find many supernovae out before this. And what that means is that if you've got evolution, say, well, what happens if my Type 1a supernova are just getting fainter with cosmic time? So as I go further and further back in the universe, my Type 1a supernovae are, for reasons I don't yet understand, getting fainter. Well, what actually might happen then is I think they're further away because they're fainter, but actually they're just fainter. But what you would therefore expect to see as a test of cosmology is that when the universe transitions from acceleration to deceleration, they should start getting brighter again. So they should appear closer, i.e. brighter, again. And this is exactly what is observed. So all of those things point to the same picture. And then there's a final thing that I would like to mention, which is this idea, already briefly outlined it earlier in the lecture, of what's called a baryon acoustic oscillation. So in the early universe, pre-CMB, bound objects can't actually sort of gravitationally collapse because the pressure from them is too large. Essentially, as you squeeze them down, as they start to collapse, the pressure pushes them back out again. And so they oscillate between small and compact to large and diffuse. And I've already said that the objects that you see, the largest structures you see in the CMB, are the signature of this. But here's the thing. Once you've formed the CMB, then objects can collapse. Essentially, the fact that you no longer have the matter and the radiation entrained together after recombination, you don't have all these Thomson scatterings, means that things can collapse. And this scale, these preferred scales in the CMB are what you call frozen in. And they expand with the universe. And so what if I go and measure the redshifts for many galaxies? And if I do that, and I look at their angular structure, I will see preferred scales. And that is the first peak of the CMB multiplied by the change in the scale factor. So in other words, I have my standard ruler at a range of redshifts. And supports my benchmark cosmology. So all of that supports it. And that's not to say there aren't still questions. There are still open questions that exist in cosmology. For example, there's an unexpected tension between the Hubble constant measured by different methods. But nonetheless, this benchmark cosmology is now the one that we can really use with some confidence. And we call this lambda CDM for cosmological constant and this one is cold dark matter. So this is the universe we live in. It is a lambda CDM universe. Now, that's pretty good. That's quite impressive. I've just been through and explained how we understand, all these different components of the universe. The only issue is we don't know what dark matter is and we don't know what dark energy is. And together they make up about 96% of the universe. So we still don't know what makes dark matter and dark energy. There are a few ideas out there, and so next lecture we'll go and look at what we actually think might make dark matter. So, thank you, that's all for this week.